Hello. Today we're going to talk about topic 3.2, implicit differentiation. So the first thing we need to kind of understand is what does it mean to have an implicit relation as opposed to an explicit function. So and pretty much everything we've done up to this point has been y equals or f of x equals or some sort of function notation where you only have one output variable, in this case normally y. Implicit relations occur when we may have more than one variable or where it might become very difficult to write your equation as y equals, or it might not even satisfy the function, the vertical line test to be a function. So if you take a look at this little table at the top, on the left hand side, in green here we have a quadratic, we have this radical function. Those are both explicitly written functions. But on the right-hand side in gray, you have things that are implicit. You have things that are written in terms of x's and y's, or I should say written in terms of two variables. We don't need to limit it to just x and y. So we want to talk about how to take the derivative of y, and how that works, especially when we have more than one variable. So if you take a look at example 1, that's kind of the old problem that we did. If I take d over dx means to differentiate with respect to x, I'm going to get a 3x squared using my power rule as my derivative. Okay, now I'm going to come back to this problem and I'm going to explain, the difference between the two. But for answer B, your answer is not 3y squared. Okay, we do take the derivative very similarly, but I want you to look at the outside. We're supposed to be taking the derivative with respect to x. There are no x's in my problem. There's a y. So when I take the derivative of y cubed, I started off with a 3y squared, the same way I would with x. However, I now need to take the derivative of the y, so that's going to give us this little rate of change next to it. That dy dx has to be part of my problem. So my answer is a 3y squared times dy dx. Okay, now let's go back to the previous problem, the x cubed. Why did we not have to put a little dy over dx on that one? What's the difference? Why does it being y, matter? So when you do this power rule, if I take the derivative of the power, I'm going to drop the power down, lower the degree, and you're actually going to get, we're taking the derivative of x with respect to x. Now, do you notice how we have a dx over dx? Well, anytime you have the same thing in the numerator and denominator, that's just 1. So whenever we're taking the derivative of a variable with respect to that variable, in this case, we're taking the derivative of x with respect to x, okay, you don't really need to write that rate of change next to it. However, when we're taking the derivative of a different variable, like in part B, we're taking the derivative of an expression of y with respect to x, it means that we need to include that dy dx. And that ultimately, that comes from a chain rule, right? So just to kind of outline this a little further, we have a y cubed. I'm going to take the derivative with respect to x of y cubed. So I start with my outer piece. The 3 comes down, the inside stays the same. But I now need to take the derivative of the inside, which the derivative of y is 1, but because it's a y, we are going to get a dy over dx, and that is our derivative. In this case, we can just write it as a 3y squared times dy dx. So let's do a few more, just so you can see how it works here. So for part C, we have sum or difference rule, which means I can write this by taking the derivative of x plus the derivative of y. Now notice I put d over dx, right? It's kind of like I distributed that onto the inside. So the derivative of x with respect to x is 1. And if you wanted to, you could write a dx over dx plus the derivative of y is also 1, but we would get a dy over dx. And we can't really simplify that. So dx over dx is just 1, so I'm going to get a 1 plus, and I would write this as dy, over dx. And this would be my derivative. Okay, let's do another one. I'll change colors here. Try to make it colorful. So now for part D, I have a product rule. So I'm not doing the sum or difference. I need to use that product rule. So I'm going to start, remember, take the derivative of the first. So I have, just so you guys can see, I'm doing x times y squared. So I'm going to, I just want to keep good notation here. Okay, I'm going to start by taking the derivative of x, which would be 1, dx over dx, but you don't really need to write that, times, keep the second the same, plus, now I'm going to keep the first the same, times the derivative of the second, so I used a little power rule, but because that was a y, you get this rate of change, this dy over dx. You only get the dy over dx when you take the derivative, when you use one of those power rules, or when you use one of those formulas that we've been doing. That's the only time you get a dy dx is when you take the derivative of y with respect to x. So if I write this a little neater, I'm going to have a y squared plus x times a 2y times a dy over dx. Okay, now I have seen some textbooks, just so you can see it. I always like to write things multiple ways. X times 2y times y prime. I've also seen that, if you like. Now, I prefer the dy dx because it's very detailed on, I'm taking the derivative of y with respect to x. It shows both. Y prime doesn't really show me that, but that is also an acceptable answer. All right, so I have some kind of guidelines here. We're going to differentiate both sides of the equation with respect to x. That's always, step number 1. We're going to collect all the terms involving dy dx to one side, okay? And then we're going to factor it out, and we're going to solve it for dy dx so we can get our derivative. So I want you to show you how this works here. So again, 4 steps. The biggest one is just taking the derivative appropriately. So if you take a look at example 2, I want to find dy over dx. I want to take the derivative with respect to x of this function. Now, I'm going to use good notation here. I'm going to take the derivative with respect to x of both sides. And remember, what we do to one side, we do to the other. Okay? So now if I take the derivative of a y cubed, I'm going to use a lot of sum and difference rule here. I'm going to drop the 3 down. Let me change colors. So 3 y squared, but because it was a y, it gets a dy dx, plus, now the derivative of y squared, which is my next term, would be a 2y, again, gets a dy dx, and then the derivative of a negative 5y is a negative 5. Again, there was a y in that. It doesn't matter that it's not there anymore. The fact that it started with a y, it gets a dy dx, and then the derivative of the x squared is a minus 2x. And that's going to equal, now we have to take the derivative of the right side of our equation. So the derivative of negative 4 is just 0 because the derivative of any constant is 0. So here's what I'm going to do. I am going to solve this, because again, we have to get dy dx all by itself. Okay, I am going to add 2x over to the other side. So I get a 3y squared times dy over dx plus a 2y times a dy over dx minus a 5 times a dy over dx equals 2x. Now I'm going to factor out that dy over dx, which gives me a 3y squared plus 2y minus 5 equals a 2x. And then you can divide that expression over. So my derivative, my dy dx, is equal to a 2x divided by a 3y squared plus 2y minus 5. And this is my answer. Okay? So again, kind of go through these steps if you remember seeing these steps in the beginning. I'm going to differentiate both sides. I'm going to collect all the terms involving dy dx to one side. Okay? Factor it out, divide it to get your dy dx all by itself. Okay? So let's take a look at example 3. Same idea. I tried to incorporate some chain rule to keep practicing that. That's what this unit is kind of all about. So I'm going to take the derivative of both sides. So d over dx of sine of xy. Make sure my parentheses are good. And what I do to one side, I have to do to the other, right? So I got to take the derivative with respect to x of 10x. So I start with the outer piece of my function. Derivative of sine is cosine. But then I need to take the derivative of the xy and x times y, and that's a product. So I'm going to get a product rule here. Okay, so I'm going to take the derivative of the first, keep the second. If you notice, I haven't really taken the derivative of y yet. I took the derivative of sine, I've taken the derivative of x. Okay, but now when I do the other half of my product rule, I'm going to keep the x, but now when I take the derivative of y, I get a dy over dx, or a 1, right? Derivative of y is just 1, and because it's a y, it gets a dy dx. Okay, and then that equals derivative of 10x is 10, and I don't need anything after that because it was an x. It was an expression of x. You could put a dx over dx after it, but you don't really need it because dx over dx is going to be 1. So let's start to see what I get here. I'm going to have the cosine of xy times y plus x times dy over dx equals 10. Okay. Again, my goal is to get dy dx all by itself. So what I can do here is I can divide. So a y, let's get this bracket all alone here. You could distribute if you wanted to, be about the same number of steps. So I get a 10 over cosine of xy. I'm going to subtract the y. Let's change colors. I need to give myself a little bit more room. So I'm going to have an x times dy over dx equals a 10 over cosine xy minus y. And then I need to divide both sides by x. So I get a dy over dx equals, now if I divide both sides by y, I need to divide both of those terms. So I'm going to get a 10 over x cosine of xy, and then minus y over x. This would be the derivative of that implicit relation. Okay, so the big idea here is we're taking the derivatives the same way. We're using the same formulas. You just need to be careful when you take the derivative of an expression of y that you have to put a dy dx at the end of it. Okay, so now you're going to see a lot of the same problems that we've covered before. So for part A, right? So just so you can get an idea, I give you this relation. I don't know if you're familiar with it at all, depending on how much you remember of conic sections from pre-calculus. But let's say I were to divide 4 to both sides. I get x squared over 4 plus y squared over 1 equals 1. This is going to be an ellipse. So again, I don't know, what you remember, but I just want you to be able to see a graph. My major axis would be 2. My minor axis would be in the y direction of 1. It's centered at the origin. So this would be my graph. Now, you can type this into Desmo, so it'll give you a quick graph of this if you wanted it. But I just wanted you to have a visual of what we're looking at. So let's find the derivative of this implicit relation. So I'm going to take the derivative with respect to x of both sides. Okay, and I'm trying to keep my notation nice. So I'm showing my mathematical steps, right? D over dx of the left side and the right side. So that's going to now give me a 2x. I don't need a rate of change because it is an x, plus an 8y, but because it's a y, I get a dy over dx, and it equals the derivative of 4, because that's a constant, just gives me a 0. So now I want to get dy dx all by itself. So I'm going to have an 8y times dy over dx is equal to a negative 2x. And then divide the 8y. So I get a negative 2x over 8y. And if you want to reduce that, you can say a negative x over 4y. That would be appropriate. So now it says find the slope of the tangent line at the point square root of 2, comma, negative 1 over square root of 2. So they give you an x and a y value. So you know the slope of any tangent line can be found using that derivative. Okay, so now if I want the slope at this point, okay, I can use those coordinates and I can say negative square root of 2 over 4 times a negative 1 over square root of 2, because that's my y value. Now I'm going to try to clean that up a little bit. I'm going to say a negative square root of 2 over a negative 4 over square root of 2. Now I can multiply by the reciprocal here. Right, which gives me a negative 2 over a negative 4, or a positive 1/2. So the slope at that point is going to be a positive 1/2. Now, just so you're aware, that point is right around here somewhere, just so you're aware. And the slope of this point is going to be about a positive 1/2. And that makes sense. That looks actually pretty close, from where I put my point on the graph. But we know the slope has to be this value. Okay. Now write the equation of the tangent line. Well, to write the equation of any tangent line, we need a point and a slope. Well, they gave us the point, right? So I'm going to say y minus, actually in this case, plus 1 over square root of 2 equals a 1/2 x minus square root of 2. And then just get your y all by itself. So I have a 1/2 x minus square root of 2 minus 1/2. And this minus 1, sorry, 1 over square root of 2. You do not need to rationalize that denominator. That does not make a difference. Okay, this is the equation of that little tangent line, that purple tangent line that I drew. Okay, so just one more time, find the slope of the graph for the relation below, right, at the point 3, 1, right? So now I tried to incorporate as much of the pieces as I can. Not to confuse, but just to show how things connect. So if you notice, I have an x squared plus y squared, but it's all squared. And on the right-hand side, you have to be very careful. They like to throw this xy in there. That's a product, so we have to use product rule when we get to the right side. So if I start this, I'm going to use a power rule. So drop the 2 down. 6x squared plus y squared. But now I need to do the derivative of the inside. So the derivative of the x squared is a 2x. The derivative of the y squared is a 2y. But I'm going to get a dy dx because, again, I'm taking the derivative with respect to x, and that expression was a different variable. Now I want to take the derivative of the right-hand side. So the 100x is just going to be 100 times, keep the second the same, plus, now keep the first the same, and take the derivative of y, which is a dy over dx. Okay, so let's clean up what I got here. I'm going to start distributing a little bit, a 6x squared plus 6y squared times 2x plus 2y times dy over dx equals 100y plus 100x times a dy over dx. Now our goal is to find dy dx here, to find the slope. So they gave me a point. So rather than try to simplify this, let's plug this point in to see what I get. Whoa, sorry about that, guys. So if I plug 3 in there for x, I'm going to get 6 times 9 plus 6 times my y squared. 1 squared is just 1. 2 times 3 plus 2 times 1, and that has a dy over dx, equals 100 times 1 is just 100, plus 100 times 3 is a 300 dy over dx. So I got 54 plus 6 is 60 times a 6 plus 2 dy over dx equals 100 plus 300 dy over dx. So I'm going to distribute. I'm going to say 360 plus 120 dy over dx equals 100 plus 300 dy over dx. And I'm going to now get all my dy dx terms to one side and my constants to the other. So if I subtract 100, I get 260 equals, I'm going to subtract a 120 dy over dx. So minus 120 dy over dx. So that gives me a 180 dy over dx on the right side. Divide your 180. So I know dy over dx is going to be 260 over 180. You can reduce that to 26 over 18. You can reduce that to 13 over 9. This is the slope of the tangent line at that point. So 3, 1 on our graph is right here. Okay, the slope of this tangent line is going to be 13 over 9. All right. Now, just kind of a reminder for this, horizontal and vertical tangents, right? So horizontal tangent lines have a slope of 0, or where the derivative is 0. Vertical tangents have a slope that's undefined. The only thing with vertical tangents is you have to make sure that that point was originally on your problem, right? So it was really part of your relation already. So make sure that it wasn't a corner or a cusp to begin with. So if you have a location for the horizontal tangents, well, I need to take the derivative. So the derivative of 3x squared, let me write my problem out here real quick. So the derivative of 3x squared is a 6x, plus the derivative of 2y squared is a 4y, include your dy over dx, and then the derivative of 16 is 0. Let's get dy dx all by itself. So I'm going to have a 4y times dy over dx, and that is equal to a negative 6x. And I get a negative 3x over 2y. I reduced that fraction a little bit, but that's the derivative, right? So where are the horizontal tangents? So if you know the derivative is going to be a negative 3x over 2y, right? Oops, I wrote 3y over 2y. My fault, guys. Where is the slope of this tangent line going to be horizontal? Well, anytime I'm given a fraction, this fraction is going to be 0 when the top is 0. So all I really need to do is set a negative 3x equal to 0. I need to solve it. And if you divide that negative 3, I know I'm going to have a horizontal tangent when x is 0. So I'm going to take that 0. I'm going to substitute it back into my original problem. So 3 times 0 squared plus 2y squared equals 16. I have 0 squared is 0 times 3 is still 0, so I have a 2y squared equals 16, or a y squared equals 8, and y equals plus or minus the square root of 8. Now, if you want to reduce that radical, okay, you can. You don't need to, but I get plus or minus 2 square root of 2. So my horizontal tangents, my answer to this problem is x 0, comma 2 square root of 2, and 0, comma a negative 2 square root 2. These are the 2 points. There are 2 points where I have a horizontal tangent on that graph. Okay, which makes sense because it's an ellipse. So you'll have horizontal tangents on the bottom and top of that ellipse. So let's take a look at the vertical tangents, right? So I already took the derivative. I'm going to use the derivative from part A. So I already know dy over dx is a negative 3x over 2y. So in this problem, vertical tangents are where it's undefined. So I'm going to take this 2y and I'm going to set it equal to 0. If you solve it, you're going to get where y is 0. Okay, so I just need to find the x values for where that happens. So if I do that, I'm going to substitute in. Let me change over to my green pen. So I'm going to have a 3x squared plus 2 times 0 squared equals 16, or a 3x squared equals 16. Divide the 3, I get x squared equals 16 over 3, which is going to give me x to equal plus or minus the square root of 16 over 3. And if you want to write that a little better, you can say plus or minus 4 over square root of 3, because we know what the square root of 16 is. So I know my x and y values now. So to write my answer, I know that I'm going to have vertical tangents at 0, I'm sorry, that was the y value. Let's write that correctly. X first. Always x first. So a positive 4 over square root of 3, comma 0, and a negative 4 over square root of 3, comma 0. These are the locations of my vertical tangents. So just kind of recall, horizontal tangents are where the slope is 0. If you have a fraction, your slope is always going to be 0 when the numerator is 0. Okay. Vertical tangents are when my slope is undefined. So that's going to be, if I have a fraction, it's going to be where my denominator is 0. Okay. So I just have one more example here. Determine the location of all the horizontal and vertical tangents. So if I take the derivative of x squared is 2x. Derivative of x is 1. Derivative of a 2y squared is a 4y, but because it's a y, it gets a dy dx. And the derivative of 8 is 0. So now if I subtract this over, let's get dy dx all by itself. I'm going to have a 4y times dy over dx equals a negative 2x minus 1, because I subtracted those terms to the other side. Divide by that coefficient, I get a negative 2x minus 1 all over 4y, and that is my derivative. So my horizontal, let's try to color code this the best I can. My horizontal tangents, okay, are going to be when the negative 2x minus 1 is equal to 0. So if I add the 1, divide the negative 2, I'm going to get where x is a negative 1/2. Okay. So if I plug that in, negative 1/2 squared plus 1/2 plus a 2y squared equals 8. So I have a 1/4 plus 1/2, which will be a 3/4 plus a 2y squared equals 8. Subtract 3/4. Oh boy. Okay. 2y squared equals, if you subtract 8 minus 3/4, what's that going to be? 29 fourths. think that's right. Okay, let me double check on my calculator here. I don't want to put something up that's wrong. Yeah, 29 over 4. Divide the 2, which gives me a y squared equals 29 over 8. Square root both sides. I get y to equal plus or minus the square root of 29 over 8. You don't need to reduce that, but I know my horizontal tangents are at a negative 1/2, comma, square root of 29 over 8, and a negative 1/2, comma, a negative square root of 29 over 8. And there are 2 places where I have horizontal tangents. Now, if I go to my vertical tangents, I'm going to set the denominator equal to 0. So for vertical, I have my 4y equals 0, y is equal to 0. So if I plug that into my equation, I have x squared plus x plus 2 times 0 squared equals 8. Or an x squared plus x equals 8. Now it's a quadratic. Let's get it all to one side. Okay. Of course, it's not a good quadratic. It's not going to factor. So you might have to use some quadratic formula. In this case, ladies and gentlemen, I'm going to call this a calculator question. I'm going to put it into my calculator. I'm going to say x squared plus x minus 8. I'm going to graph it. I'm going to find the zeros of that graph. So let's see what I get here. So I'm going to go the first 0. Okay, again, you could use quadratic formula if you want. I know that the first 0 is going to be at, let's get my pen working, negative 3.372, comma, 0, because again, the y value was 0 from that point. And then the other value of where that quadratic will be 0 is going to be at a 2.372, comma 0, always 3 decimal places. And this is the location of your vertical tangents. All right. Now, just to finish off this video, there is one more thing I want to kind of put in here, and this is something called logarithmic differentiation. Okay. And I want to show you when we need to use it and when we don't. There's a special type of problem that applies to implicit differentiation. That's this logarithmic differentiation. So I have 4 problems here. There's one here that is unlike the others, something that we haven't discussed. So if you take a look at the first one, the derivative of e over e, those are just both constants. E to the e is a constant, and the derivative of any constant is just 0. Okay. For part B, the derivative of e to the x, well, that's one of the common derivatives we learned, is still e to the x. The derivative of x to the e, well, that's just power rule. I'm going to drop the e down, x to the now e minus 1, okay, which looks like a weird exponent, but that would be my new exponent. Okay, that's my answer. So it's part D that is unlike the others, and I want to show just this real quick. It doesn't come up very often, but I want you to be prepared for it if it does. Is this variable to a variable power, okay? So what I'm going to do is off to the side here, I'm just going to call it y equals x to the x power. And I'm going to take the natural log of both sides. Okay. Now, one of the properties of natural logs is I can drop that exponent down as a coefficient. Okay, so I have something like this. Now, what I'm going to do is I'm going to take the derivative of both sides, all right? And then after I take the derivative of both sides, if I solve it for dy dx, it gives me my answer. So the derivative of my left side, natural log of y, well, remember, derivative of natural log is 1 over the argument. but because it's a y, it's going to get a dy dx. And then on the right side is a product rule. So I'm going to take the derivative of the first times the second plus keep the first times the derivative of the second. Let's clean this up a little bit. I have a 1 over y times dy dx equals the natural log of x, and then x times 1 over x is just 1. So it doesn't look too bad. Now, if I get that dy dx all by itself, I need to multiply both sides by y. So I'm going to have the natural log of x plus 1 times y. Oh, I messed up my parentheses here. Something like that. There we go. Okay, now to get my answer, now there were no y's in my original problem, but I want you to remember that y was x to the x power, right? I kind of circled down the top. So my derivative is going to be the natural log of x plus 1 times x to the x power. Okay, and this is the derivative. So whenever you have a variable raised to another variable, we have to use something called logarithmic differentiation. And to do that, we're going to take the log of both sides. I use natural log always just because it's the easiest to work with. But you could use a log of a different base if you prefer. But I'm going to take the log of both sides, use the properties of logs to get that exponent out of there. And then I have product rule, quotient rule, stuff like that. But I can get to the derivative. So if you look at example 9, very similar. Okay. I give you this function y equals x to the 2x. So you can see I have a variable raised to a variable power. That's a problem, right? So I'm going to take the natural log of both sides. Oops, let me write my problem correctly here. All right. Now, when you have an exponent in a log, we have a property that says we can make that a coefficient. Okay. Now I can take the derivative of both sides. The derivative of natural log of y is 1 over y. But because it's a y, we get a dy over dx. And then I have a product rule on the right-hand side. So I'm going to take the derivative of the first, keep the second, plus keep the first times the derivative of the second. And if I clean that up, I have a 1 over y times dy over dx equals a 2 ln of x plus 2x times 1 over x is just 2. I'm going to multiply both sides by my y. So I get y times 2 natural log of x plus 2. And then I'm going to plug my y back in of what the original problem was. So my dy over dx is just a x to the 2x times 2 ln of x plus 2. Okay, and that's how you do logarithmic differentiation. Again, it doesn't pop up a lot, but it does pop up every so often. So I just want to kind of show you how that works. But in order to do it, you have to know how to use this implicit, how to take the derivative of y's rather than x's, right? So just kind of a heads up. So in future problems, in topics beyond this one, we're going to take the derivative of functions, or I should say relations, that have multiple variables in them, okay? So if you have multiple variables, we need to figure out what we're taking the derivative with respect to, and any variable that does not match that is going to get a rate of change at the end of it, okay? So again, the purpose of this is this implicit differentiation of all of these problems today were just x's and y's, but you can have x's, y's, z's, w's, any variable you like. And if you take the derivative of those variables, we just need to include a rate of change. Okay. Hopefully this was helpful. If you have any questions, please email.